Okay, to determine polarity of a whole molecule, you first need to determine the bond polarity. And to do that, you need to know the electronegativity differences between the atoms. The second thing you need to determine overall molecular polarity is to use the correct molecular shape and 3D structure. So if we take ammonia, NH3, as an example, I calculate the bond polarities here. So that's the electronegativity difference between each bond. In this case, they're the same bonds, nitrogen and hydrogen. There's just 3 of them. So each electronegativity difference is 0.9. That puts us in the polar bond region. Now again, these ranges are guidelines. Sometimes you'll see some polar bonds that are above 1.7, like hydrogen and fluorine. But in this example, we are squarely in the polar bond region. So because each of these bonds are polar, we can draw dipole moments for them, and we show them by these arrows. We can also depict them as a delta plus and a delta negative. We need to make sure that we're putting the delta negative at the most electronegative atom. So nitrogen is 3.0, hydrogen is 2.1, 3.0 is larger. That means that nitrogen wants to have more electrons around it more than more than hydrogen does. So the nitrogen is going to tug on the electrons in the bond, and they're going to live around the nitrogen more often than they do around the hydrogen. They're still being shared in the bond, though. It's just an unequal sharing. So now that we have this delta negative positives by the hydrogens and delta negatives by the nitrogens, and we know that the overall shape of this structure is trigonal pyramidal because we have a steric number of 4, but there is a lone pair present, so that's going to push the bonds closer together. That tells us that all of these vectors are all pointing slightly towards the nitrogen. Because they're all going kind of in the same direction, they're going to add, and the overall polarity of the entire molecule is going towards the nitrogen. That means this overall molecule is polar, and this is important because it helps us explain things like differing boiling points between molecules. It helps us explain the phases of matter based on what the matter is made of, the molecular makeup of the matter. And polarity also comes into play when we talk about chemical reactions. It's often a driving force in how molecules react with each other, because based on the polarity, they're going to orient with each other in a certain way, because you now have these mini magnets happening, and that's going to cause attractions at different parts of molecules. Now, for an example of nonpolar molecules, things like diatomic molecules that have the same element are always going to be polar because it's the same number minus the same number. It's always 0 for the delta electronegativity. So this molecule O2 is overall non-polar. You can have an example like this where we have carbon and fluorine. The delta electronegativity for each of these 4 bonds is fluorine 4.0 minus 2.5. That's a 1.5, which is clearly a polar bond. But because the molecular shape is tetrahedral, because there are no lone pairs, the bond polarities going out towards the fluorines are all going in the same exact opposite directions, which means that they cancel out. So the overall polarity of this whole molecule is nonpolar, despite the fact that it has polar bonds. Hopefully this helped. Let me know if you want more examples.